Hi students, in this video we are continuing our discussion of elasticity questions. Let's take the next question. This question is there, a wire can withstand a maximum force of 500 Newton. One wire is there which can withstand maximum force of 500 Newton. Say for example, this is the wire and if we apply a force of 500 Newton, then it may break, right? 300 Newton applied, it won't break. 400 Newton applied, not break. But 500 Newton, it will break. So its breaking strength or breaking tension is equal to 500 Newton. Now, they are saying what maximum force a piece of it can withstand if it is cut into 5 equal pieces, 5 identical pieces. It has been cut into 5 pieces. Cut into 5 pieces. And then each piece can withstand how much force without breaking? This is what we have to find. Now, in this type of question, generally, they don't mention clearly how the wire has been cut. We can cut the wire in 2 ways. One is this way, 1, 2, 3, 4, 5. This way. Means this is one piece, this is another piece, this is another, this is another, this is another. So in that case, we have one such piece. And what is the maximum force it can withstand? We will see. Another possibility is we divide it, we break it in this way. Lengthwise it has been cut this way. Means I'll make a little thicker one. This is the wire. This piece cut. This piece cut. This piece cut. This piece cut, right? Only one piece means this, means thickness has been reduced. For both the cases, answer will be different. For both the cases, answer will be different. Here first I will explain you the concept and then I will tell you how to solve this question. I hope the situation is clear. Very simple question this is. And very common question, almost in every book you will get. But try to understand what is the concept. One wire is there, it can withstand maximum force 500 Newton. It is cut into 5 equal pieces. Then one such piece can withstand how much force? I am trying to say this wire can be cut in 2 ways. One this way and one this way. So what is the concept? First you see that. Here the concept is breaking stress. Breaking stress. Already I have told you about this in the theory class. The maximum stress a material can bear without rupturing. Rupturing means breaking. Is termed as breaking stress. We denote it by sigma B. Is termed as breaking stress. It is a property of the material. It is independent of shape, size of object, and it depends only on the nature of material. Right? I will suggest, I have told you only in short in the theory class, you can write this also in the theory part. So breaking stress is the property of the material and it is the maximum stress a material can sustain without breaking. That is the breaking stress, right? Now, coming back to the question. Now, let us say we have one wire. One material whose breaking stress is sigma B. Then a force has been applied F on it. Then the stress developed will be equal to F by A. If we say the cross section area of this is A, then the stress developed is F by A. For not to break, for wire not to break, the stress developed must be less than breaking stress. F must be less than sigma B into A. Now the applied force which can break the wire, depends upon the breaking stress and cross section area. For the same material, breaking stress is same, but cross section area may be different. Now you see, we have this wire. For this, breaking force is 500 Newton. If we cut in this way, then cross section area is not changed. Breaking stress is not changing. So the required force to break any piece, the maximum force which any particular part of the wire can withstand without breaking will be same as 500 Newton. But if we cut into 5 pieces in this way, then the cross section area of one part will become 1/5 of this cross section area, and the new breaking force will come out to be sigma B into A by 5, and sigma B into A is 500, so 500 by 5, that is 100 Newton will come. I hope the things are clear to you. A very exclusive concept type question. I hope you have understood. Let's take the next question. In most of the books, answer will be given as 500 Newton because they assume that this wire has been cut in this way, but wire can be cut this way also. Remember this. Next question you take. We have one parallelopiped cuboid type thing. Cuboid. Length L, height C, or say H, and width B. Young's modulus Y, Poisson's ratio sigma, and it is under tensile stress, force F. Object is under tensile stress. Now we want to see in this length increases, volume increases, and area decreases. This is what we are going to see. Now here, sigma is equal to minus, when we are increasing it, then B and H are going to change. Length increases and B and H will decrease. So sigma can be written as change in B by B upon change in length by L, and this can also be written as minus delta H by H upon delta L by L. Let us say on applying this force, length, breadth and height, they changes by dl, db and dh, delta L, delta B and delta H. Then by using the sigma ratio we got this sigma into delta L by L is equal to delta B by B, and this is also equal to delta H by H. We got this. Now volume is equal to LBH, dV by V equal to dl by L plus dB by B plus dH by H. Substitute the dB by B and dH by H here. You will get dl by L is common, 1 minus 2 sigma. As sigma is always less than 1, experimentally we have seen this. So dV by V is equal to 1 minus 2 sigma. 1 minus 2 sigma will be positive from here, we can say. So equal to dl by L into a positive number. In the tensile stress, length is increasing, so volume also increases. In tensile stress, length increases, so volume also increases. Similarly, for compressive stress also we can say, for compressive stress, this will be negative. That's why this will be also negative. So, in the theory part we have seen that in the tensile stress, length and volume increases while the area decreases. And in the compressive stress, length and volume decreases while the area increases. That only we have proved it. Let's take the next question. Consider a rod of length L, mass M, cross section area A, Young's modulus Y, placed on a smooth horizontal surface. This is placed on a smooth horizontal surface. A force F is acting on it, and we want to find the elastic potential energy stored in the rod, right? So this is what we'll find. At a distance x, we'll consider a small section of width dx. Then tension at this point, first of all, our task to find. From Newton's second law, acceleration is equal to F by m. Then tension at this particular location will be found by using the Newton's second law, F minus T equal to ma. M is F minus T equal to m. M is m by L into x into A. You will get A is equal to F by m, substitute. So tension you got F minus m by L into x into F by m, that is F into 1 minus x by L. This you got the tension T at this location. Tension T at this location. So what is the elongation in this? Elongation in this will come out to be y equal to tension at this location. Stress is T by A. T by A upon change in dx upon dx. Like in the last video, the last question what we have discussed, similar to that. Delta dx by dx is equal to T by Ay, F into 1 minus x by L upon Ay. Right? Now what we have to find? the energy stored. What is the energy stored in this small part? Energy stored in this small part. Du is equal to half stress in this. Stress in this is T by A. Strain in this is this one, T by AY. And volume of this is A dx. Understood? Now, what we have done? First we have found the acceleration, then we have found the tension at this particular location. Then we have written the Young's modulus expression for this particular small part. From there we got the strain developed in this. Then the energy stored in this will be half into stress into strain into volume. Now this comes out to be, substitute the value of T here and you will get half T. T is equal to F into 1 minus x by L whole square. It is T square. T square is F square into 1 minus x by L whole square upon AY into dx. This is the energy stored in this part. Total energy stored will be integral of du, that is f square upon 2ay is common, integral 1 minus x by L whole square dx 0 to L. Integral will be 0 to L. Now integrate this expression, f square upon 2ay into integral of this will be L by 3, f square L by 6ay. This is your answer, right? Let's take the next question. This is also a very nice question. We have one thin walled steel tube of radius r and thickness delta r, and thickness is very small as compared to delta r, like a hollow pipe type of thing. And we have to find what is the maximum excess pressure inside that tube so that tube won't rupture, tube won't break. What is the maximum pressure we can have? Say for example, this is a tube and if we apply the more pressure will be there, it can rupture. So what is the maximum pressure inside so that it won't rupture? Excess pressure means difference between the inside and outside pressure. And it is also given that breaking stress of the steel is sigma b. So what is the maximum pressure inside a thin walled tube so that it won't break? This is what we have to find. Options are there, you can note down the question. Now we are solving it, right? Now consider the tube like this is the tube. This radius is r and this thickness is delta. This thickness is delta r. And here some pressure will be there. Say excess pressure is delta p. What we have to find? If we see the cross section view, if we cut it from here and we see it from this side, then we'll see it like this type of thing, right? Now this is something like, you can say this is the tube like this, and we are cutting it from here and seeing, then we'll see this only. Now here the pressure is there, here pressure force will be there, pulling it like this, right? Now this pressure force will be causing the stress to develop in this particular material. This material is there, here the stress will develop. Let us say at this particular part tension is T. Internal restoring force is T on this cross section. And this small part is subtending an angle 2 theta at the center. Then this force cancelled, and this direction, the net force comes here, this direction 2t sine theta. And because of this excess pressure delta P, a force is acting here, delta P into area of this section. Now what will be the area that you have to understand? We have this type of thing. Our element is this strip, right? This strip, like this it is coming. Length is L and this width is R 2 theta. So area of the strip will be, it is into the board, like this it is coming. So area of the strip will be this length, which is equal to R into 2 theta, and this depth sig L. Since it is in equilibrium, this will be balanced. So 2t sine theta is theta, because theta is small, equal to delta P into 2 theta into RL. 2 theta cancel, and the tension we got, the internal restoring force what we got is delta P into RL. Now this restoring force is developing where? We have taken this element. Now T is developing on this cross section, this way. So what will be this area? This thickness into this length. This thickness is delta R. So the stress here is T by delta R into L. T upon delta R L is delta P R L upon delta R into L. L cancelled. This is sigma. For not to rupture, stress has to be less than sigma B. So delta P R by delta R must be less than sigma B, and you have the maximum excess pressure is equal to sigma B into R by delta R. This is your answer. Again, a very nice conceptual questions, right? That's all for now, because we have discussed sufficient number of questions. You will be able to solve most of the things. Now, as a practice, you can try the SCV questions and J trainer questions. Okay? Then in the next class we'll meet.